this is physics group 85.
And I'm Kelsey Holian.
And I'm Robert All, and then today we present you the simple harmonic motion. So basically what the simple harmonic motion, it's also called oscillatory motion, which basically means objects move around an equilibrium point, and then it's a periodic movement, so it go up and down or back and forth, which brings to two situations that we're looking at. One is a simple pendulum that I showed you at the beginning of the movie, and then the second one is going to be at the spring. So usually it's around a equilibrium point, and they go back and forth, and then based on the gravity or the spring constant, it changes its velocity. There's two other things that you have to look out for. There's period. The period stands for the time it complete for one cycle, complete cycle of motion, and then frequency, it just how many cycles it's in 1 second. And then there's another thing that we're looking at is called a angular velocity, which we have the formula right here. It's omega, it's the weird W looking one, is equal to 2 pi f. 2 pi means the circumference of the motion, and then f stands for frequency. And also you can read it as the square root of g over L. G stands for gravity and L for the length of the string. We're looking at a pendulum in this situation, and as you can see that there's no mass involved, so it really doesn't matter how heavy your object is, the simple harmonic motion is still going to go.
So today's problem, a 450 gram object is attached to a 60 centimeter long string, oscillates as a pendulum. It has a speed of 0.15 meters per second as it passes through the lowest point. What maximum angle does the pendulum reach? Assume the angle remains small, in which case the model is simple harmonic motion. So first we have to solve for the angular frequency of the pendulum. We're going to use omega equals 2 pi f equals the square root of gravity over the length of the string. So omega equals the square root of gravity over the length of the string, which would equal the square root of 9.8 meters per second squared all over 0.6 meters, which equals 4.04 radians a second. So that is the angular frequency. Second, we need to find the speed at the lowest point. So A equals max speed equals max velocity over omega, which would equal the speed at the lowest point over the angular frequency. Equals 0.0371 meters. Finally, we determine the maximum angle at the maximum arc length at the fastest speed is max of theta equals max speed over the length of the string, which would be 0.6 which would equal 0.062 radians, which is roughly 3.6 degrees. So because it's less than 10 degrees, our analysis based on the small angle approximation is reasonable. So it is simple harmonic motion.
Hi, and welcome to Simple Harmonic Motion Part 2. This time we'll be showing you how to do a spring problem. So, we're given an air track glider is attached to a spring pulled 20 centimeters to the right and released at t equals 0 seconds. It makes 15 oscillations in 10 seconds. So what they want to know is what is the period of oscillation, what is the object's maximum speed, and what are the position and velocity at t equals 8 seconds. So, part A asks what the period of oscillation is, and to find that, we need to find the frequency, which is 15 oscillations divided by 10 seconds. We come out to get 1.5 oscillations a second. We take that and plug that into our t equation, which is 1 over f, which is 1.5, and we get 0.667 seconds. That's our period. Then moving on to part B, we're looking for what the maximum speed is. So our oscillation amplitude is A equals 0.2 meters, and thus we plug it into our equation for velocity max, which is 2 pi A divided by t. We plug in our variables, which is 2 pi times 0.2 over 0.667 seconds, and we come out to get 1.88 meters a second.
Alright, so now we're trying to find the position and velocity when t is equal to 8 seconds. So first we're finding the position, which is given by the equation x is equal to a times cosine of omega t. And omega t just comes out to be 2 pi t over the period. And so what you want to do is plug and check all the numbers that were given, which is the a, our t, and our period. And once you plug all that in, you get 6.25 centimeters, which is what the position is at 8 seconds. Then we want to find velocity, which is given by the equation negative velocity max times the sine of omega t as well. And you plug and check all the numbers that were given as well, at, and you get negative 179 centimeters per second.